The universe seems silent because we are too far away and too small to hear what happens in it. But silence is not proof of emptiness. Each star is a natural nuclear power plant operating for billions of years, and each stellar system provides energy in unimaginable quantities for us. If there is intelligence beyond Earth, it too had to deal with the same central problem: how to capture, convert, and control energy without destroying its own basis for survival. Nikolai Kardashev proposed an idea that avoids guesses about appearance or culture, measuring civilizations by how much energy they can use in a controlled manner. This makes advancement something physical and comparable. Energy sustains industry, transportation, information, agriculture, defense, and space exploration. The greater the energy control, the greater the capacity to reshape the environment and survive crises. The scale does not describe intentions. It describes available power and dominance over energy flows. Humanity appears powerful when viewed from space, but our consumption is still a tiny fraction of what the sun delivers to the planet. Moreover, we depend on vulnerable networks. Blackouts, storms, droughts, and conflicts can quickly disrupt energy and logistics chains. This contrast reveals our true position. We are technological, yet energy limited. The Kardashev scale acts as an uncomfortable mirror because it shows that modern does not mean energy maturity or guaranteed civilizational stability. Human history can be read as a sequence of energy revolutions. Fire enhanced nutrition and safety. Coal and steam multiplied mechanical power. Electricity allowed for fine control and communication. Nuclear opened up enormous energy densities. Each leap increased productivity and risk at the same time. That is why Kardashev did not ask what machines we use, but how much energy we are capable of managing. The scale arises from the understanding that technology is a consequence, and energy is the foundation. The sun releases an absurd amount of energy every second by earthly standards. Imagining a civilization that captures a significant fraction of this flow is to envision orbital engineering, large-scale space industrial automation, and asteroid mining. It's not magic. It's thermodynamics, materials, logistics, and time. Physics allows us to capture light and convert it into useful work. The real obstacle is organizing such complex systems without catastrophic failures and without socially collapsing in the process. Energy growth tends to accelerate at the beginning because extra energy creates better tools, which unlock more energy. However, exponential growth encounters limits: residual heat, environmental impacts, resources, social instability, and technological risks. Energy maturity is not about consuming more indefinitely. It is about growing and stabilizing, reducing systemic vulnerabilities. A civilization that does not learn this may fail before reaching high levels on the scale. Therefore, the scale also suggests a filter. Surviving one's own growth may be rare. When we think of progress, we usually focus on inventions. Kardashev raises another question. What is the total energy budget of civilization, and how reliable is it? Large-scale renewable sources, robust storage, and smart grids are essential steps to reduce vulnerability. A civilization that controls energy needs redundancy and distribution. It's not enough to generate power, it must deliver power with stability, even during crises. This separates an advanced civilization from a luck-dependent civilization. The planetary energy control requires planetary knowledge. Sensors, satellites, and models allow for predicting extreme events and adjusting infrastructure before collapse. Real-time data turns into strategic decisions: where to store, how to distribute, when to reduce load, how to protect critical systems. A mature civilization treats climate, oceans, and geology as components of the same energy system. This does not mean controlling nature with arrogance, but understanding limits and operating within them, reducing impacts and increasing resilience. The Kardashev scale broadens the horizon. If energy defines capacity, then the cosmos offers steps far beyond the planet. Stars, accretion disks, and gravitational phenomena are colossal sources. A civilization may start limited to the ground, then use orbit, and later explore resources from the stellar system. This path does not depend on ambition. It depends on physics and survival. When the planet becomes a limit, space becomes the solution. And when space becomes routine, the star becomes the next logical energy budget. This changes the search for life. Instead of just looking for messages, we search for technosignatures. A civilization that uses a lot of energy leaves physical traces, variations in brightness, excess infrared, patterns that do not match dust, planets, or common stellar activity. The focus shifts to thermodynamics. All technology generates waste heat. If energy consumption is high, thermal emission is also likely to be high. Even if no one wants to communicate, physics can reveal activity. A Dyson sphere is often imagined as a solid shell, but a distributed swarm is more plausible. Millions of independent collectors that grow over time. This allows for maintenance, expansion, and fault tolerance. Each module captures energy and converts it into electricity, controlled heat, or industrial work. The result can alter the light observed from the star. Some of the visible brightness is blocked, and some reappears in the infrared. It is a type of signature that astronomy can investigate. The infrared is a fundamental clue, because residual heat is inevitable. There is no technology with perfect efficiency. A civilization that manipulates energy on a large scale needs to dissipate heat to avoid destroying its own systems. This can create a thermal excess compared to what is expected for a star and its planets. In simple terms, there is leftover heat. Searching for this leftover is searching for activity, and this is elegant because it is independent of culture, language, or intention. It depends only on physics. Advanced civilizations are not just energy. They are energy organized into information. Computing, logistics, climate modeling, industrial automation, and science require constant power and efficient cooling. The more a civilization calculates and coordinates, the more energy it consumes to keep the system's mind functioning. Therefore, information becomes a measurable component of the energy budget. On a large scale, the collective intelligence itself may have a thermal signature. The question, is there life? Also becomes, is there processing, control, and abnormal thermodynamic waste? A common mistake is to confuse advancement with gadgetry. Kardashev treats advancement as stable infrastructure. A civilization can have incredible breakthrough technologies and still be fragile if its energy is unstable or concentrated. Stability means redundant networks, efficient distribution, recovery capacity after shocks, and governance capable of coordinating billions without collapsing. This social dimension appears indirectly in the scale. Without coordination, there is no safe planetary or stellar energy capture. Energy amplifies power, but it also amplifies the consequences of failures. Growing energetically increases exposure to threats, solar storms, impacts, cascading failures, and conflicts. A mature civilization needs to protect satellites, networks, and storage against space weather and rare events. This requires planning and redundancy, but also extra energy reserved for contingencies. In other words, part of the energy budget becomes insurance against the universe. Civilizations that cannot afford this insurance may fall. Therefore, in searching for technosignatures, we also look for signs of resilience. Large systems that persist long enough to be observable. To expand energy, many civilizations would need raw materials from outside the planet. Asteroid mining and processing in orbit reduce environmental pressure and provide rare metals. This also changes the growth pace. Production can occur where energy is captured, avoiding costly transportation. Automation is almost inevitable because space is hostile and distant. In this scenario, biological presence may be small. The infrastructure may be mostly robotic. Still, energy consumption leaves a mark. The universe does not see who operates. It sees what is consumed and dissipated. Abundant energy makes it plausible to build artificial habitats with simulated gravity and controlled environmental cycles. This does not require colonizing planets immediately. It requires building environments where energy and matter are managed precisely. A civilization that creates large-scale habitats also creates new energy demands: lighting, life support, artificial agriculture, total recycling. Again, the Kardashev scale does not say how they live, but indicates that to sustain these systems, the energy budget needs to rise and remain stable for a long time. Not every anomaly is technology. Dust, disks, comets, and stellar variability can mimic artificial signals. Therefore, the search for technosignatures requires a method. Compare data, eliminate natural hypotheses, observe repetition and consistency. The Kardashev scale helps because it defines what would be necessary energetically for certain effects. We don't need to bet on stories. We need to ask if the observed signature is compatible with thermodynamics and large-scale engineering. When nature fails to explain, technology becomes a legitimate hypothesis, not a guess. One advantage of thinking about energy is that we can look across multiple bands: visible, infrared, radio, and beyond. A civilization may not deliberately transmit radio signals, but it cannot escape the thermal balance if it consumes massive energy. This makes infrared especially important. Additionally, light-blocking patterns may arise in the visible spectrum. Combining these signals reduces false positives. The Kardashev scale, therefore, is not just a philosophical idea. It is an observational strategy to search where physics compels traces. Capturing energy is half the challenge. Transporting and using it is the other half. In space, cables are not practical over long distances, so concepts like beam transmission arise, microwaves, or lasers. Each method has losses and risks, and this appears as additional residual heat. An efficient civilization needs to minimize losses, maintain alignment, and prevent catastrophic failures. The larger the scale, the greater the need for automation, redundancy, and safety protocols. Stellar technology is not a trick. It is a permanent industrial system that needs to operate for decades and centuries. The scale also raises an uncomfortable question. How many civilizations last long enough to leave detectable traces? On Earth, civilizations have collapsed due to resources, wars, and instability. On a technological scale, the risks increase. More powerful weapons, greater environmental impacts, dependence on critical networks. Perhaps the universe is filled with interrupted attempts. If this is common, the absence of signals does not prove the absence of life. It proves that persisting may be the great challenge. Kardashev forces us to consider duration as part of advancement. Energy also becomes protection. Diverting an asteroid, hardening infrastructure against solar storms, building global redundancy, and creating strategic reserves require power and coordination. A civilization that wants to survive needs to spend energy to reduce risks, not just to grow. This means that the energy budget is not only for comfort, it serves to ensure continuity. Civilizations that ignore defense and resilience can be eliminated by rare events. Therefore, thinking about energy is thinking about survival, and survival is what allows for the accumulation of enough technology to ascend the scale. Energy and environment are inseparable. When a society increases power without protecting its ecological base, it accumulates vulnerabilities that return as crises. A civilization that ascends the scale must learn to produce, store, and distribute energy without degrading the planet, because environmental resilience is invisible infrastructure. This applies even to civilizations that intend to go into space. If the home planet collapses early, the project dies early. Therefore, the Kardashev scale implicitly points to systemic maturity, energy with stability, and stability with respected limits. In essence, the Kardashev scale is not a prediction of the future. It is a way to organize possibilities. It defines energy tiers that seem plausible according to physics: planetary, stellar, galactic. Each tier requires time, resources, and survival. When we look at the cosmos with this ruler, we change the type of question. Instead of asking, "Where are the ships?" we ask, "Where are the signatures of energy capture and dissipation?" This makes the search more scientific, and at the same time, more demanding. The Kardashev scale functions as a conceptual map for thinking about stellar civilizations without relying on loose imagination. It connects our still limited reality to scenarios where energy is captured and managed at much higher levels. By adopting energy as a universal language, the search for intelligent life gains direction, looking for physical patterns incompatible with common natural processes. At the same time, we gain a diagnosis about ourselves. Advancing on the scale is not just about technology, it is stability, resilience, and sufficient historical continuity to transform potential into a lasting civilization. A Type 1 civilization abilities. Today, extreme weather events show how fragile we are. Networks fail, supply chains break, and entire regions are exposed. A Type 1 civilization invests energy to reduce risk, not just to grow. Real-time monitoring, advanced forecasting, and redundant infrastructure allow us to absorb shocks without collapsing. The goal is not to control the climate out of vanity, but to maintain social and economic stability in the face of a dynamic and unpredictable planet. Large-scale solar energy is the most direct way to expand the energy budget without polluting. However, collecting energy is only half the problem. A Type 1 civilization needs efficient transmission, smart grids, and storage to handle night, clouds, and seasonality. By integrating distant regions, it compensates for peaks and valleys in production, ensuring stability. When the system functions like an organism, energy flows where it is needed, without waste and without relying on makeshift solutions. Diversifying sources is essential to reduce vulnerabilities. Wind, tides, and ocean currents complement solar and decrease dependence on a single matrix. This also geographically distributes generation, reducing the risk of cascading failures. In a Type 1 civilization, energy is viewed as a portfolio, multiple sources, various distribution routes, and multiple layers of storage. Energy stability arises from redundancy, not from betting on a single technological miracle. The leap to the planetary level requires coordination. Smart networks adjust load and production in real time, prevent blackouts, and isolate failures before they spread. Sensors detect abnormal heating, overloads, and losses. At the same time, management needs to be secure, because integrated systems can be targets for attacks and sabotage. A Type 1 civilization combines power with cybersecurity and rapid recovery protocols. Energy at this stage is both engineering and strategy. Storage is the backbone of stability. Without it, intermittent sources create chronic vulnerability. A Type 1 civilization masters multiple technologies: high-density batteries, thermal storage, green hydrogen, and gravitational solutions. This ensures supply even when production drops. Energy reserves become equivalent to reserves of water and food, a mechanism for civilizational security. With robust storage, society stops living on the edge and gains the ability for reliable planning. Abundant energy transforms food production. Efficient irrigation, controlled fertilization, and continuous monitoring reduce waste and increase productivity. Vertical farming and greenhouses can operate near urban centers, decreasing transportation and losses. A Type 1 civilization does not rely on climatic luck to feed billions. It uses energy to stabilize production chains. This does not mean artificializing everything, but making the food system resilient to droughts, floods, and temperature fluctuations that can cause severe crises today. Cities at the planetary level function as efficient ecosystems. Buildings generate part of their own energy, waste is recycled, and residual heat is repurposed. Electric public transportation reduces pollution and improves efficiency. Lighting, climate control, and consumption are optimized by intelligent systems. The goal is to reduce the energy cost per inhabitant without compromising quality of life. The more efficient the city, the more energy is available for science, planetary defense, and critical infrastructure, strengthening long-term social stability. A Type 1 civilization develops planetary consciousness through sensors and models. It measures everything: temperature, humidity, currents, carbon, biodiversity, and water quality. Data turns into preventive actions, such as early fire containment, watershed protection, and network reinforcement before storms. This reduces costs and prevents collapses. The available energy allows for a quick and broad response, but the key is reliable information. Without data, power becomes waste. With data, power becomes resilience. Water is a civilizational bottleneck. With abundant energy, desalination and advanced treatment become viable on a large scale. Distribution networks can reduce losses and ensure supply even in dry regions. This decreases conflicts and increases stability. Furthermore, efficient sanitation reduces diseases and increases productivity. A Type 1 civilization invests energy to make critical resources predictable. When water and energy are stable, society gains long-term capacity, reducing vulnerabilities that have historically toppled civilizations. Nuclear fusion, if mastered, is a game changer. Clean, constant, and high-density energy would drastically reduce dependence on polluting and unstable sources. In the context of a Type 1 civilization, fusion would be part of the matrix, not the only solution. It would provide baseload power to keep networks and industry running continuously. However, even with fusion, thermal management and safety remain critical. The goal is not just to generate energy, but to do so with stability and controlled risk. Using energy on a planetary scale also means protecting the planet. Detecting and diverting asteroids requires sensors, computing, and, in some cases, physical intervention capability. A Type 1 civilization allocates budget for defense because rare events can be existential. This also includes protection against solar storms that can disrupt networks. Resilience is part of the energy package. Energy is not just for comfort, it serves for continuity. By reducing external risks, civilization increases the chance of surviving long enough to develop even greater infrastructure. Information consumes energy. Digital networks, artificial intelligence, climate simulations, and logistical coordination require constant power. A Type 1 civilization has the capacity to maintain large-scale computing without overloading the planet, thanks to efficiency and clean energy. This strengthens data-driven governance, reducing blind decisions. At the same time, it increases the need for cybersecurity and redundancy. When everything depends on information, protecting digital flows becomes as important as protecting transmission lines. Environmental balance is infrastructure. Without healthy ecosystems, the climate becomes unstable, water becomes unpredictable, and agriculture suffers. A Type 1 civilization uses energy to protect and restore, not just to exploit. Reforestation, monitoring, and rapid-fire response reduce damage. Preservation stops being a discourse and becomes an energy strategy. Keeping the planet stable is keeping the energy budget base functioning. Without this base, the entire system becomes vulnerable to cascading crises. Efficient logistics reduce consumption and increase economic stability. With clean energy, public transport and cargo can operate with low environmental impact. Automation optimizes routes and reduces waste. In a Type 1 civilization, the planet functions as a synchronized network, where production and distribution are coordinated to avoid scarcity and excess. This reduces social tensions and improves quality of life. Energy here is the invisible foundation of a stable economy, not just a technical input. Redundancy is the rule. Planetary networks need to keep functioning even with local failures. This implies multiple transmission routes, isolation systems, and rapid maintenance. Type 1 civilization avoids single points of failure. It also creates strategic stocks of critical components and recovery protocols. When the system is large, Small failures can turn into gigantic crises. Therefore, engineering blends with planning. Energy stability is not having energy. It is ensuring that it remains available under stress. Matter and energy are partners. Material waste becomes energy waste because extracting, transporting, and processing consumes power. A Type 1 civilization adopts a circular economy, advanced recycling, reuse, and design for durability. This reduces pressure on ecosystems and improves overall efficiency. With less waste, more energy is available for research, health, education, and defense. Furthermore, reducing dependence on rare raw materials decreases conflicts and instability, strengthening the civilizational capacity to remain cohesive over long periods. The oceans are part of the energy and climate system. Currents, temperature, and biodiversity influence the entire planet. A Type 1 civilization continuously maps and monitors oceans, preventing ecological collapses and maintaining balance. Abundant energy allows for efficient oversight, recovery of degraded areas, and in-depth research. Furthermore, ocean energy can be explored carefully without destroying habitats. When the planet is viewed as an integrated system, oceans cease to be a distant frontier and become critical infrastructure. Stable energy also supports health and science. Hospitals, cold chains, drug production, and research depend on reliable supply. In crises, energy saves lives. A Type 1 civilization reduces health vulnerability with resilient infrastructure and efficient logistics. This is not just well-being, it is the ability to maintain a productive population and functional institutions. When energy fails, everything fails. Therefore, energy stability is a condition for social stability. And social stability is a condition for maintaining long-term projects, essential for progress. Education is an indirect energy accelerator. Training technicians, scientists, and engineers increases efficiency and reduces failures. A Type 1 civilization invests in knowledge as part of the energy system. Better maintenance, better materials, better governance. With a broad educational base, society avoids decisions that compromise the future for immediate gain. This improves political and economic resilience. Energy and knowledge mutually reinforce each other. The more knowledge, the better the use of energy. The more energy, the greater the capacity to produce knowledge, creating a virtuous cycle. A Type 1 civilization signal is distribution. Energy should not be concentrated in a few islands of wealth while large regions remain vulnerable. Balanced planetary networks reduce extreme inequality, decrease conflicts, and increase cohesion. This is not idealism, it is social engineering for stability. When entire regions are left out of the system, they become points of permanent crisis. A civilization that wants to endure must integrate. Energy integration leads to civilizational integration. Stability depends on reducing structural tensions that can implode the system. Growing energetically increases exposure to space weather. Solar storms can damage satellites and cause blackouts in long networks. A Type 1 civilization prepares with shielding, redundancy, controlled shutdown protocols, and rapid recovery. It also monitors the sun and predicts dangerous events in advance. Extra energy is reserved for contingencies. This defense mindset is part of maturity. It is not enough to expand, it is necessary to protect what has already been built, because the universe does not offer guaranteed stability. The ability to restore ecosystems on a large scale shows real mastery, not just exploitation. Energy enables the movement of water, the recovery of soils, the restoration of rivers, and the reversal of some accumulated damage. This strengthens climate, agriculture, and water security. A Type 1 civilization understands that the stability of the planet is the main asset. Without a stable planet, networks collapse, economies break down, and long-term projects die. Therefore, restoration is not a luxury. It is a strategy to keep the entire system operating for centuries, with predictability and reduced risk. No limit, a Type 1 civilization is a state of planetary energy stability. It does not need to grow exponentially, it needs to maintain balance. Clean energy, robust distribution, storage, protection, and data-driven governance sustain continuity. This is the stage at which a species stops being a hostage of the planet and becomes a responsible manager of the system. It does not mean perfection, but it means sufficient resilience to survive shocks, learn from failures, and maintain long-term projects without collapsing. Reaching the planetary level is making energy a predictable and manageable good, as if the planet were a complex machine operating in dynamic equilibrium. At this stage, civilization reduces existential risks, integrates infrastructure, and improves overall efficiency. More importantly, it creates time. Time for advanced science, for defense, for space exploration, and for building systems that do not rely on improvisation. The Kardashev scale addresses this. Not just power, but the capacity to maintain power with sufficient stability to continue existing. A Type 2 civilization no longer thinks in terms of planetary energy, but rather in stellar energy. This means capturing a significant fraction of stellar power and transforming it into useful work for industry, computing, habitats, and exploration. The star is a fusion reactor that operates for billions of years, offering long-term stability. The challenge is not just technological, it is logistical and systemic. To build infrastructure that operates continuously, tolerates failures, and manages residual heat without collapsing. Instead of a solid shell, the more plausible model is a swarm of collectors, millions of independent modules that grow over time. This allows for maintenance and gradual expansion. Each unit captures light, converts energy, and transmits it to other systems. The whole can alter the appearance of the star, blocking part of the visible spectrum and increasing emission in the infrared due to dissipated heat. This thermodynamic signature is a powerful observational clue for searching for technosignatures. Building stellar infrastructure requires raw materials on an industrial scale, and space offers this in abundance. Asteroids can be dismantled and refined by robotic systems, without relying on atmospheres or strong gravity. This reduces energy costs and allows for production close to the site of use. A Type 2 civilization likely automates almost everything: mining, manufacturing, assembly, and maintenance. Even if the biological presence is small, the infrastructure reveals high and continuous energy consumption. Orbital construction changes engineering. Without strong gravity, enormous parts can be assembled with less structural stress, but they require precise motion control and alignment. Assembly robots operate with redundancy, replacing faulty modules and expanding the swarm. The key is scalability. Start small, prove stability, and grow over decades. A Type 2 civilization does not build all at once. It cultivates infrastructure like one builds a city, always adding layers and capacity. Capturing energy is just the beginning. Distributing energy is the nervous system of stellar civilization. Instead of cables, transmission can occur through beams of microwaves or lasers, with fine alignment and safety protocols. Inevitable losses turn into residual heat, requiring radiators and thermal management. Failures can be dangerous, so the network needs redundancy and automatic control. The higher the power transferred, the greater the need for stability and error tolerance. Stellar energy requires controlled risk engineering. Thermodynamics imposes hard limits. Every energy conversion generates heat. On a stellar scale, thermal dissipation becomes the biggest operational challenge because accumulated heat can destroy modules and destabilize the grid. Therefore, giant radiators, emissive surfaces, and load distribution are essential. Part of the size of a Type 2 civilization may simply be infrastructure for safely disposing of heat. This also creates an observable signature: excess infrared consistent with artificial energy consumption. With abundant energy, artificial habitats can multiply. Cylinders or rotating rings generate artificial gravity, allowing biological life in relative comfort. Life support requires constant energy, water recycling, atmosphere control, agricultural lighting, and climate control. A Type 2 civilization may prefer habitats over planets because habitats are custom-built and can be distributed throughout the star network. The more habitats there are, the greater the energy demand, and the greater the need for coordination to avoid systemic failures. The space industry changes the energy economy. Manufacturing close to the energy source and near the raw materials reduces transportation and losses. This encourages an industrial ecosystem in orbit: refineries, industrial printers, assembly lines, and maintenance centers. Automation reduces the need for direct biological intervention, but increases dependence on computing and sensors. A stellar civilization resembles a network of autonomous systems that operate continuously, adjusting to failures and reorganizing production according to demand. From our point of view, a Type 2 civilization can be detected by changes in the light of the star. A swarm of collectors produces different transit patterns of planets. Variations may be irregular, but still consistent with multiple structures. Furthermore, if part of the energy is converted and dissipated, the star appears hotter in the infrared than it should. Combining signals across multiple bands helps to separate dust and natural phenomena from plausible technological hypotheses. The infrared is the language of inevitability. Technology can hide intention, but it cannot hide thermal balance. If a civilization consumes stellar energy on a large scale, it needs to dissipate heat somewhere. This heat escapes as infrared. Looking for excess in this band is searching for what remains after efficiency. This reduces dependence on radio signals and increases scientific rigor. A robust technosignature is one that nature poorly explains and thermodynamics explains well. A stellar civilization also needs to deal with the violence of the star. Coronal mass ejections, energetic particles, and brightness variations can damage modules and habitats. This requires shielding, smart positioning, and shutdown protocols. Abundant energy allows for building protection, but protection consumes mass and complexity. The network needs to keep functioning even under stress, isolating affected regions and redistributing load. Resilience is as important as capture, because a cascading failure can compromise the entire infrastructure. Stellar-scale logistics is a problem of its own. Thousands or millions of modules in orbit require traffic control, collision prevention, and constant maintenance. This requires sensors, computing, and automatic coordination standards. It is not enough to build, it is necessary to operate. A Type 2 civilization may have algorithmic authorities that manage routes, maintenance windows, and energy redistribution. The larger the network, the more important it becomes to avoid small errors that, when accumulated, lead to large-scale disasters. In addition to asteroids, moons can provide useful materials: ice for water and fuel, metals for structures, silicates for components. A Type 2 civilization explores the system as a set of resources, distributing mining to reduce risks and bottlenecks. This also allows for redundancy. If one region suffers an extreme event, others maintain operation. The logic is the same as planetary networks, but expanded. Multiple sources, multiple paths, multiple stocks. Stability arises from diversity and distribution. Stellar-scale computing can become a major energy consumer. Simulations, industrial coordination, science, and automation require constant power. In orbital environments, cooling can be planned with radiators, but it is still limited by thermodynamics. This creates an interesting balance. The more a civilization computes, the more heat it needs to dissipate, and the more infrared it emits. In other words, operational intelligence translates into thermal signature. The search for life may turn into a search for abnormal scale processing. Reliable communication is essential for coordinating a star network. Optical beams or high-frequency links connect modules, habitats, and factories. Signal delays exist and need to be managed by local autonomous systems. The network operates as a federation of nodes. Each node makes quick decisions and global coordination maintains consistency. The greater the distance, the more important autonomy becomes. This changes the concept of society. Part of the decisions can be made by automated systems, ensuring continuity and reducing the risk of collapses due to delays. On a stellar scale, failures are inevitable. Modules burn out, micrometeoroids puncture, components degrade due to radiation. Therefore, maintenance needs to be automatic and constant. Repair robots and diagnostic systems replace parts like an industrial routine. The secret is fault tolerance, losing units without compromising the whole. When the system is large, stability comes from modularity and quick replacement. This also reinforces the plausibility of the swarm. It grows and renews continuously, maintaining operation even under permanent wear. A Type 2 civilization can look beyond its own star system, but its strength lies in consolidating local dominance first. Stellar energy allows for sending probes, building advanced propulsion, and maintaining long missions. Even so, interstellar space is vast and expensive. Therefore, expansion can be gradual: automated probes, industrial seeds, and remote exploration. The important thing is that stellar energy makes these choices possible. The limit shifts from insufficient energy to time and logistics on a much larger scale. Distinguishing nature and technology is difficult. Dust disks can mimic light blockages, and variable stars can confuse readings. Therefore, the search needs to combine data: light curve, spectrum, infrared, and stability over time. A technological swarm tends to produce patterns that change with maintenance and expansion, yet still follow an energetic logic. The technological hypothesis gains strength when natural phenomena require increasingly improbable explanations. Kardashev provides the context. Large effects require large energy budgets. Radiation is a constant enemy in space. A stellar civilization needs resilient materials, shields, and architecture that minimize exposure. This increases mass and complexity, but abundant energy helps to produce and transport protection. Still, total shielding is impossible. Therefore, redundancy and repair are essential. The system needs to accept wear and continue. This operate under damage mindset is part of stellar maturity. It's not about avoiding problems, but about having the systemic capacity to absorb and continuously recover. A Type 2 civilization can reduce the visible light from a star because it intercepts photons for energy use. At the same time, it increases thermal emission by dissipating heat. This shift of energy from the visible to the infrared is a plausible and searchable signature. It is not definitive proof, but it is a rational target. Observing this pattern in many systems and comparing it with natural models may reveal candidates. Science does not need to assert it's alien. It only needs to identify it's anomalous and investigate rigorously. The most impressive aspect of a stellar civilization is not a single event, but continuity. Operating for decades and centuries requires political, economic, and technical stability. Long-term projects survive generations, crises, and failures. This implies governance capable of maintaining priority and large-scale coordination. A stellar network is as social as it is technical, even if automated. Without institutional stability, infrastructure becomes orbital ruin. Therefore, level Type 2 suggests not only power, but long-term maturity. Stellar energy enables science on an unprecedented scale. Distributed telescopes, long-distance interferometry, and advanced instrumentation can map exoplanets in detail. This could accelerate the very search for life, because a Type 2 civilization has the ability to observe the universe with far greater accuracy than ours. Paradoxically, this also means that it can become discrete if it wishes. However, even discretely, it still needs to dissipate heat and maintain infrastructure. Physics remains our best ally. The energy balance cannot be erased. In everyday life, a stellar civilization is a continuous operating system. Modules collect energy, factories produce parts, habitats consume resources, and robots keep everything running. The routine is prevention, detecting failures before they become cascades. This type of operation requires extremely high standards of quality and control. The larger the network, the more systemic discipline is needed. This creates an aesthetic of engineering: modularity, redundancy, maintenance, and predictability. The Kardashev scale at this level ceases to be theory and becomes a practical description of an industrial ecosystem in orbit. For us, Type 2 civilization is an observational hypothesis, a stellar system with consistent signs of energy capture and dissipation. The most important signature is not an intelligent signal, but a coherent physical pattern over time. When we see light blocked in a complex way, infrared above expected levels, and enough stability to persist, we find a candidate. This does not prove artificial origin, but directs research. The Kardashev scale acts as a filter. Large signatures require large energy budgets. Type 2 civilization represents the transition in which the star becomes infrastructure. Energy is no longer limited by climate and geography and becomes an industrial network in space. This level requires automation, logistics, thermal management, and long-term stability. Thinking this way, we understand why technosignatures should primarily exist as waste heat and anomalous brightness patterns. The search for intelligent life is not about seeking messages, but about looking for physical consequences of a monumental energy consumption sustained over a long time. A Type 3 civilization operates on a galactic scale. This means managing energy and matter distributed across billions of stars, with logistics and coordination that exceed our intuition. It is not just more energy, it is a network that spans immense distances and remains functional for ages. To reach this point, it would require not only advanced technology, but also extreme historical stability. A galactic civilization needs to persist long enough to spread infrastructure, maintain maintenance, and integrate very different systems. If a Type 2 civilization transforms a star into infrastructure, a Type 3 transforms many stars into nodes of a network. Each system can have collectors, factories, and habitats, but the real challenge is integration. Enormous distances impose communication delays and transportation costs. Therefore, the network needs to be decentralized, with local autonomy and common standards. The galaxy becomes a distributed industrial ecosystem, where each node operates robustly and shares knowledge, resources, and redundancy. Galactic expansion, if it occurs, likely depends on automation and slow, persistent processes. Sending biological populations over long distances is difficult, but sending industrial seeds is more plausible. Autonomous probes could arrive, use local resources, build infrastructure, and replicate part of the system. Over millions of years, this could create a growing mesh of nodes. The hallmark of a Type 3 civilization would be continuity, a process that never stops, always expanding and renewing itself. A galactic civilization depends on local industry in each system. Transporting matter between stars is expensive, so each node needs to be self-sufficient in materials, maintenance, and production. This requires deep automation and modular standardization, allowing for repair and replacement with local resources. The main product may be infrastructure, energy collectors, computing, communication, and protection. The network grows because each node can build the next one. In this logic, growth does not depend on unique events, but on controlled industrial replication over eras. How to detect a Type 3 civilization? In principle, by large-scale signatures. If many star systems have collectors and thermal dissipation, the galaxy could exhibit excess infrared in specific regions. Statistical patterns of brightness could deviate from what is expected for natural stellar populations. It's not simple because dust and star formation also emit infrared. Therefore, the approach is to compare distributions, where the emission is too high, too consistent, or too organized for known natural processes. A challenge is that nature also produces complex signals. Dust, nebulae, and star formation generate intense infrared. Therefore, a galactic civilization would need to leave a distinguishable pattern, perhaps related to organization, regularity, and correlation with mature stellar structures. For example, thermal excess in regions where there has been no recent star formation would be suspicious. The idea is not to look for an alien beacon, but rather statistical inconsistencies on a galactic scale, where engineering and thermodynamics may stand out. Coordination on a galactic scale requires robust communication, but the speed of light imposes limits. This pushes civilization towards decentralized models, local decisions and global protocols, instead of instantaneous central command. The network can function as a federation of autonomous nodes, aligned by goals and standards. Messages travel but arrive late. Therefore, stability depends on autonomy and consistency. This structure resembles an ecosystem more than a central government, and it is precisely this that can make it enduring for ages. In a Type 3 civilization, the diversity of stars and environments is enormous. Red dwarfs, sun-like stars, multiple systems, regions with high radiation, and calmer areas. The infrastructure needs to adapt to each context, maintaining safety and efficiency standards. This suggests a level of engineering that is not only grand but highly flexible. The galactic network operates as a collection of adaptive solutions, where accumulated knowledge allows for the construction and maintenance of habitats in very varied conditions without losing stability. Galactic-scale threats may include nearby supernovae, gamma-ray bursts, stellar encounters, and dense clouds that alter environments. A Type 3 civilization would need alert systems, redistribution, and even infrastructure migration. Abundant energy allows for protection, but time and distance complicate response. Therefore, resilience is built in advance. Redundancy, dispersion, and the ability to relocate operations to less risky areas. Civilization survives because it does not depend on a single location. It is distributed, and distribution is protection. A plausible characteristic is slow and continuous expansion, accompanying galactic dynamics. The civilization may prefer stable regions, avoid areas of high radiation, and operate in zones where resources are abundant. Over millions of years, this creates patterns of occupation and infrastructure. From our point of view, this may appear as strange correlations between stellar age, thermal emission, and the absence of natural phenomena that explain the pattern. The signature of a galactic civilization is more statistical ecology than an isolated signal. Computing can be a dominant use of energy on a galactic scale. Simulations, coordination, science, and automation require continuous processing. Where there is computing, there is heat. Therefore, in principle, a Type 3 civilization could create regions with increased infrared emission due to large processing complexes. Again, this is not proof, but it is a physical hypothesis. The difference would be organization, persistent patterns in regions where nature does not predict extra heat. Searching for structured heat is searching for large-scale technological activity. One idea discussed in astrophysics is to look for gaps or unlikely regularities. If a civilization alters many systems, it may create effects such as reduced brightness in specific stellar populations, or changes in the distribution of light in certain regions. However, the galaxy is complex, and many natural causes create patterns. Therefore, the strategy is statistical. Compare many galaxies, look for repeated anomalies, and model natural hypotheses. Only then does the technological hypothesis come in as a plausible alternative, guided by energy and thermodynamics. On a galactic scale, maintenance is not a task. It is a permanent industry. Modules fail, collisions occur, radiation degrades materials. To maintain the network, each node needs replacement factories and repair robots. This reinforces the idea of modularity. Civilization does not rely on unique parts. It depends on replicable standards. When everything is modular, the network can survive local losses without collapsing. This type of operational stability, repeated over billions of kilometers, is what characterizes a truly galactic civilization. Even with local production, some interstellar transport may exist for high-complexity items or for the transfer of knowledge and industrial seeds. However, transport is slow, so the system needs to function without it most of the time. This requires local autonomy and stockpiles. The galactic network operates as a set of regional economies, with limited and planned exchange. Stability depends on avoiding fragile dependencies. In other words, civilization does not matter survival. It produces survival at each node, with enough redundancy to withstand. Time is a central component. Type 3 civilizations, if they exist, may operate over periods that make human history seem like an instant. This means traversing stellar changes, orbital migration, and galactic evolutions. A durable network requires planning for scales that exceed generations. It may choose to operate more intensively in stable stars and less in dangerous stars. Over time, this creates a map of preferences that can be statistically detectable. Regions where the apparent energetic activity is too high for the age and stellar environment. In practice, searching for Type 3 civilizations requires extensive astronomical surveys. We observe millions of stars and thousands of galaxies, looking for patterns that deviate from the expected. The Kardashev scale provides a guide. The greater the energy, the higher the chance of leaving traces. This does not guarantee detection, but it helps prioritize efforts. The challenge is that the galaxy is complex noise. Therefore, science works with probabilities and models. A galactic signature will not be an obvious signal, but a persistent statistic that resists natural explanations. Natural phenomena can mask or imitate technological signatures. Dust can obscure stars and generate infrared, and the spiral structure itself produces patterns. So what makes a technological hypothesis plausible is the combination of signals: thermal excess where there is no star formation, regularity on large scales, persistence over time, and correlation with mature stellar populations. Looking for a single clue is fragile. Looking for a coherent set is robust. The Kardashev scale serves to think about energy coherence, not coincidences. A frequently discussed expansion mechanism is replicative automation. Probes that arrive, use local resources, and build new probes and infrastructure. This does not require invasion, it requires persistence. If this process occurs over millions of years, it can cover large regions of the galaxy. The critical point is control. Replication needs to be limited, secure, and goal-oriented to avoid chaos. A Type 3 civilization would have to master not only energy, but also the governance of autonomous systems on a colossal scale, maintaining predictability and stability. If many systems have collectors and dissipation, the combined effect may appear as thermal halos in specific regions. Still, detecting this requires separating dust, star formation, and other processes. Therefore, observation in multiple bands and comparison between galaxies become essential. The technological hypothesis gains strength when the pattern is rare and difficult to explain naturally. The Kardashev scale suggests that if highly advanced civilizations exist, they will not be point-like. They will be distributed, and the distribution may generate large-scale signatures. A hypothetical effect of massive capture is the reduction of visible light in certain stellar populations because part of the energy is intercepted and converted. This energy does not disappear. It reappears as heat at longer wavelengths. Thus, a Type 3 civilization could change the apparent color of regions of the galaxy by shifting energy from the visible to the infrared. This is difficult to confirm, but it is a clear physical prediction. If observations find this shift without a plausible natural cause, a new field of investigation opens up. The galactic scale is also a social scale. Even with automation, decisions about expansion, protection, energy use, and long-term maintenance need rules. Perhaps it is a culture, perhaps algorithmic protocols, perhaps a combination. The important thing is that the network needs to remain cohesive without instant central command. This suggests stable norms and lasting goals. A Type 3 civilization is not just a set of machines, it is a system of continuity. And continuity is what transforms power into civilization, rather than power into scattered ruin. In long eras, rare events become inevitable. Supernovae, gamma-ray bursts, and orbital changes can make regions dangerous. A Type 3 civilization protects itself through dispersion and the ability to relocate operations. Abundant energy allows for the construction of redundancy, but does not eliminate risk. The strategy is to make local losses tolerable. When one node fails, others sustain the network. This design philosophy is the same as resilient networks on Earth, but scaled up. On a galactic scale, resilience is the heart of the system. For us, the search for Type 3 civilizations is a quest for statistics and for persistent exceptions. We need enormous surveys, comparisons between galaxies, and rigorous physical modeling. The Kardashev scale is useful because it sets expectations. The more energy, the more likely there is to be a signature. But it also defines humility. The galaxy is complex, and natural explanations must be tested first. Science advances when it transforms speculation into falsifiable hypotheses. Searching for energy patterns on a galactic scale is one of those hypotheses. If galactic civilizations exist, they may prefer stable regions, with older stars and less turbulence. This would create a different activity map from the star formation map. Observing discrepancies between these maps can be informative. However, any conclusion requires caution. The Kardashev scale does not promise that we will see something. It suggests where to look and what kind of evidence to expect. Instead of waiting for a clear signal, we look for physical consistency, energetic coherence, and temporal persistence in observable patterns. Type 3 civilization is the idea of a galaxy partially transformed into energy and industrial infrastructure. Reaching this point requires time, automation, modularity, and governance capable of maintaining continuity over eras. For us, the best clue remains thermodynamics. Where there is monumental energy use, there is residual heat and altered brightness patterns. The Kardashev scale offers a physical vocabulary to think the unthinkable, and at the same time, a strategy. To seek consequences, not stories, and to measure anomalies with scientific rigor. When we place humanity on the Kardashev scale, the conclusion is humbling. We are not yet Type 1. We are below the planetary level, dependent on limited energy sources and vulnerable networks. This does not diminish our progress. It only shows how much we have left to transform potential into stability. At the same time, the scale offers direction. Efficiency, clean energy, storage, and resilience are real steps. The question changes. It is not just, what can we invent, but how much can we sustain without collapsing? Human energy growth has brought comfort and capability, but also risks. Complex systems break down when they depend on a few critical points. Blackouts, supply crises, and climate instabilities reveal fragility. Achieving a minimum level of energy maturity requires reducing fragile dependencies and increasing redundancy. The Kardashev scale suggests that many civilizations may fail at this transitional stage because power increases faster than control. The challenge is not to generate more energy. It is to manage energy with stability. Here arises the Fermi paradox. If the galaxy is so old and full of stars, why do we not see clear signals of advanced civilizations? The question is not just philosophical, it is statistical. If intelligent life were common and expanded rapidly, we would expect evidence. The absence of evidence may have several explanations: rarity of life, difficulty of technological survival, choices of discretion, or limitations in the way we search. The Kardashev scale helps redefine signal as energy output. A strong hypothesis is the existence of filters, difficult stages to traverse. Perhaps complex life is rare. Perhaps technological intelligence is rare. Perhaps civilizations collapse by growing too fast, trapped in internal crises and environmental risks. Or perhaps cosmic events reduce continuity, impacts, climate changes, radiation. To leave detectable traces, a civilization needs to last long enough. Thus, the paradox may be less "no one exists" and more "few persist." The Kardashev scale, in this sense, is a scale of survival as much as of energy. Our own planet shows the dilemma. Easy energy can destroy the system that sustains it. If the ecological base collapses, food chains, water, and social stability collapse along with it. Civilizations can die from poorly managed excess power. Therefore, the path to ascend the scale involves efficiency and clean energy, but also governance and social cohesion. Technology without stability becomes expanded fragility. The Fermi paradox may be a mirror. Perhaps the great obstacle is maintaining civilization, not creating technology. Many people imagine that signals from extraterrestrials would be radio waves and messages. But radio weakens, gets mixed with noise, and can be abandoned for more efficient technologies. An advanced civilization may use directional, encrypted, or simply internal communication, without detectable leaks. Therefore, searching only for radio may be looking for the technological adolescence of other species, not their maturity. The Kardashev scale suggests looking for something more inevitable: energy consumption and waste heat, because that is imposed by physics, not by choice. Technosignatures are detectable signs of technology from a distance. They can be anomalous brightness patterns, excess infrared, laser emissions, or industrial chemical signatures in atmospheres. The goal is to replace assumptions with testable hypotheses. The Kardashev scale organizes these searches by energy level. The more energy, the more likely it is to leave traces. This does not guarantee that we will find anything, but it improves our strategy. Instead of waiting for a "hello" from the cosmos, we look for measurable consequences of large-scale energy use. A highly debated technosignature is the irregular blocking of starlight, compatible with orbital structures. But nature can also produce variations: dust, comets, disks. Therefore, the correct approach is eliminative. Test natural hypotheses, observe repetitions, and compare multiple bands. If the infrared increases along with the blocking in the visible, the technological hypothesis becomes more plausible. The goal is not to quickly prove aliens, but to build a chain of evidence that withstands simple explanations and is scientifically robust. Infrared is crucial because technology generates residual heat. Any machine that converts energy into useful work produces heat as a byproduct. The higher the consumption, the greater the need to dissipate. This makes infrared an involuntary clue. A civilization can hide communication signals, but it cannot eliminate thermodynamics. Searching for thermal excess in mature stellar systems where dust is low can reveal candidates. The Kardashev scale is, in this sense, a bridge between basic physics and the strategy for searching for intelligence. Another line of technosignatures involves industrial atmospheric chemistry. Gases that would be unlikely in natural equilibrium, or combinations that suggest technological production. This is complex because geological processes can also generate rare substances. Again, the method is to compare and model. The Kardashev scale helps to think about energy plausibility. Producing certain compounds on a global scale requires energy and infrastructure. If a planet shows unusual chemical signals and also has strange thermal patterns, the pieces begin to fit into a more solid hypothesis. When we look at ourselves, we see how technosignatures can arise. Earth has nighttime brightness, radio signals, urban heat, and chemical alterations in the atmosphere. Some of this would be detectable from afar with powerful instruments. This indicates that if other civilizations exist, they may also leave traces, even unintentionally. The challenge is the distance and sensitivity. Therefore, the search must be systematic and patient, expanding observational capacity and analyzing large datasets, rather than relying on a single extraordinary event. Modern astronomy is a big data science. Surveys monitor millions of stars and billions of galaxies. This opens up space to detect rare anomalies, but demands statistical tools and artificial intelligence. Technosignatures can be subtle, hidden in noise. Unusual patterns may be discarded by inadequate filters. Therefore, part of the search for life is building analysis pipelines that preserve the strange, without confusing the strange with error. The Kardashev scale provides a map of where the strange may exist. Where energy is large, the signatures may be large. The Fermi paradox also has a cultural dimension. Our imagination tends to exaggerate the speed of expansion. Perhaps civilizations choose to grow slowly. Perhaps they prioritize stability and discretion. Perhaps they exist, but on such long timescales that coincidences are rare. Furthermore, the galaxy may be too large for easy encounters. Silence may simply be a lack of alignment between our methods and reality. That's why thinking about energy and technosignatures is useful. It reduces reliance on intentions and brings the search closer to what is physically inevitable. If there is an important filter, it may be within civilizations, not outside. Conflicts, extreme inequality, and loss of cohesion can hinder long-term projects. Abundant energy without governance becomes instability. To ascend the scale, a civilization needs to transform power into continuity, maintaining institutions, protecting infrastructure, and balancing exploitation with preservation. This is difficult because it requires large-scale coordination over a long period. The Fermi paradox may suggest that few species manage to maintain this balance for centuries and millennia, a necessary condition for leaving significant footprints. One of the best ideas of the Kardashev scale is to remember that great energy implies great engineering and great heat. If a civilization captures stellar energy, it needs to dissipate it. If it captures galactic energy, it dissipates even more. This gives us a goal: to search for infrared excess and light-blocking patterns. It's not a guarantee, but it's a strong and testable hypothesis. The universe may be full of radio-silent civilizations, yet still noisy in thermodynamics. Science can listen to that noise with the right instruments. Time is an underestimated element. Humanity has existed as a technological civilization since a cosmic instant. Older civilizations could have millions of years of advantage, but they could also have disappeared, or they may have become so stable and automated that they hardly change. Our window of observation is short. Therefore, the search for technosignatures is also a search for persistence, systems that endure for a long time. If we detect coherent patterns over decades of observation, that already suggests something beyond transient phenomena and increases scientific interest. To advance in the search for life, we need to invest in observational capacity. Larger telescopes, better sensitivity in the infrared, atmospheric spectroscopy, and continuous monitoring of light curves. Each instrumental advance expands the space of testable hypotheses. The Kardashev scale helps to guide priorities, searching for signals that grow with energy. At the same time, it reminds us that our own energy development influences how much we can observe. Science is also energy. Instruments, launches, computing, and analysis depend on a stable and sustainable energy budget. The Fermi paradox does not have a single answer. It may be that intelligent life is rare. It may be that technology quickly destroys civilizations. It may be that civilizations advance and become discrete. It may be that we are looking at the wrong signals. The important thing is that each hypothesis generates predictions. The Kardashev scale provides energy predictions. If there are large civilizations, there must be thermal traces and brightness patterns. If there are none, that also informs something about the rarity, duration, or choices of civilizations. Silence becomes data, not just a mystery. For us, the Kardashev scale is also a roadmap of priorities. Efficiency, clean energy, storage, and ecosystem protection increase resilience. This reduces the risks of collapse and creates a foundation for more ambitious projects. Reaching a level close to Type 1 means making energy predictable and manageable. This does not depend on a magic leap. It relies on a sequence of technical and institutional improvements. At the same time, this maturity can enhance our ability to detect life. More instruments, more data, and more science. Climbing the scale improves our own capacity to search for intelligence in the cosmos. The scientific method demands discipline. The anomaly is not proof of technology. Each candidate needs to be analyzed with natural hypotheses first. Dust, disks, comets, stellar variability, and instrumental effects must be ruled out. Only then does the technological hypothesis come in as an alternative. The Kardashev scale helps assess plausibility. Certain patterns require large energy and large infrastructure. If the anomaly is small, it may be noise. If it is large and persistent, it deserves investigation. The goal is to build robust evidence, not to feed easy narratives. The search for intelligent life is a project that demands global cooperation. Observatories in different hemispheres, satellites, data networks, and multidisciplinary teams need to work together. Technosignatures may appear in one part of the sky today and require confirmation tomorrow in another band. Collaboration reduces errors and increases the speed of verification. This logic connects to scale. Advanced civilizations are likely cooperative at some level because large energy projects require coordination. For us, cooperating increases the possibility of discovery, and discovering would change our perspective on humanity's place in the universe. The impact of finding technosignatures would be profound, not only to prove that we are not alone, but to show that civilization can persist and grow beyond our current state. This would change our view of the future, what is possible, what is necessary, and what risks we need to avoid. The Kardashev scale, even without discovery, is already useful because it gives us a physical horizon. It transforms curiosity into strategy and turns fear into planning. If we want to endure, we need to treat energy, the environment, and social stability as inseparable pillars. The greatest value of the scale is not to promise an inevitable destination, but to organize possibilities. Types 1, 2, and 3 are steps that require time, resilience, and systemic discipline. In seeking life, we look for signals consistent with those steps: residual heat, light blockages, industrial chemistry, and large-scale statistical patterns. By building better instruments, we refine this search. If we find something, the universe will become more inhabited in our minds. If we do not find anything, we will learn about rarity and fragility. In both cases, the scale forces us to think long-term. Placing humanity on the Kardashev scale is to recognize that we are at the beginning of a long journey. Our immediate task is to avoid traps: environmental collapse, social instability, uncontrolled technological risks. If we manage to transform energy into stability, civilization gains time to mature. Time is the most valuable resource because it allows us to accumulate knowledge, build resilience, and expand our capacity to observe the cosmos. The search for intelligent life is not just about looking outward. It is about learning to remain here, sustainably, for centuries. If you like this type of content, here's a simple challenge. Look at the sky today and remember that each star could be a world. The Kardashev scale shows that energy is the key to understanding civilizations and also to understanding our future. If we want to discover life, we need to look for technosignatures and build science with patience. And if we want to survive, we need to transform power into stability. If this cosmic journey has captivated you, like the video and keep exploring the universe with us. Follow the channel